Hey everybody. So we're starting a big discussion that's going to span many videos on the idea of area. So I want to kind of introduce a little bit how we're going to think about area and what the big problem is here, because you probably have done many of problems in the past using the notion of area, but now we want to see that it's not as easy maybe as it has been before. So let's just start with a general idea of what we think of when we talk about area, right? If I have a rectangle, let's say my rectangle is, let's call this 2 by 6 maybe, right? We know that we have this formula for area. We take the length times the width, and we would say, let's give this thing units. Let's say it was in inches. So we would say we have 2 square inches, or sometimes we use inches squared. Well, we mean exactly what it sounds like we mean. If we say this is 2 by 6, I'm saying it's 2 units long, 6 units wide. So my drawing might not be perfect. So imagine these should be more like squares, right? But it's just saying that we have 6 squares along this way and 2 squares up, and if you count them, right, you'd have 12. So again, my picture is not perfect, but that's the idea, okay? And in this case, it makes very simple sense to see what we mean by 12 square inches, that if my drawing was to scale, these are square inches, a square that's an inch on each side. Things get difficult, right, when we have shapes that aren't so easy to do this for. So for instance, right, this is not a terribly complicated shape, a circle, and we start to wonder how we're going to divide this thing up into squares to think about area, right? So we know that there's a formula, but you may not have actually stopped to think, where did that formula come from? And we'll come at it our own way. There's a method from, let's just say, from antiquity. I don't know who first came up with this method, but it's similar to what I've done with the rectangle. The idea being, you could take this circle and approximate its area by drawing a polygon inside of it, right? So however many sides this has, that sided polygon. And then you could figure out the area of this polygon, because the area of this polygon, we can use triangles, right? I'm not going to draw all of them in. It would make this drawing very difficult to look at. But there's all these triangles. You can figure out the area of these triangles. You can use some trigonometry there. And area of triangles is similar to areas of rectangles. You've probably seen pictures before where you can think of triangles as half of some trapezoid, and then the trapezoid can be chopped up. You can always kind of pull this triangles back to squares and rectangles, which makes it a lot easier to deal with and conceptualize related to this picture on the left. Well, this is only an approximation, and so what you might do next is make a better approximation. So I could, for instance, draw another triangle in here. So now you can even see that my drawing is getting very difficult to see the missing space, right? So look at, I've only done it in one section. We had, for instance, all of this missed area over here. We used to miss all that area over here, but by creating a polygon with more sides, I filled in some of that area. Right now I'm only missing this little strip here, and there's a little strip in there, but I have to divide it into more triangles. And I could do this around the whole circle and get a better approximation. And if we zoomed in close to here, we could split it up into more triangles. So this is sometimes called the method of exhaustion, and this was done by let's just say some ancient people. I think it showed up in various places, and come up with, by looking at what happens as you do this pattern over and over and over again, the number you're getting, right, for the area of the circle by adding up the areas of these triangles becomes closer and closer to something, right? We know what the area of a triangle is. If this was a triangle with a radius of 1, its area would be pi. And if you did this process, and it's not as difficult as it might sound, you might realize it might become, you might be reminded of the notion that we're getting these approximating areas that are closer and closer to the true area. There's a limit in there, right? If we keep dividing up into more and more little triangles like this, we're skipping less and less of the area that we miss. I think I did a double negative in there. We're missing less and less area. So we're getting closer and closer and closer to the true value of the area. And you could actually do a polygon on the outside as well, get an area that's larger than the circle and slowly shrinking in. Okay, so this notion is what we're actually going to use this quarter to do something even more difficult. We're going to be looking at shapes more complicated than even a circle. We're going to look at things like, right, functions, right, that can have some arbitrary curve, and we want to figure out how could we find the area under that arbitrary curve, right? Whatever function this is, okay? And we'll see that there are going to be times we can do this and times that we can't, but that's one of our goals, to figure out when can we do this and under what conditions, and then really, how do we do it? So let's look a little bit more carefully at what we're going to do, and then we'll do a little example of how to approximate. But it's going to be very modeled off of this idea. We can take a complicated shape, something with curves in it that doesn't lend itself easily to approximating, to drawing little squares in, and do some kind of regular polygon, some kind of, or some kind of polygon whose shape is very simple, right? Triangles and rectangles are pretty easy. We're mostly going to use rectangles, one of the easiest shapes we have to find the area of, right? Maybe only more difficult than a square. So let's take a look at what I'm talking about. So we're going to, here's some arbitrary function, right? So imagine we want the area under this curve, right? Meaning between the x-axis and this curve, I've just drawn a little section of a function, and we want this area. We are going to try to approximate it with rectangles. So our first approximation might be this rectangle. We just draw a rectangle, the smallest rectangle we can that covers the whole area, right? This is obviously going to be an over approximation, right? We're getting all this extra area above the curve when all we wanted was the area below. Well, we can make our approximation much better by adding rectangles, right? Here I've gone up to 3 rectangles. Notice how much better of an approximation this is. We're getting a little extra area here. We're getting a little less than we want here. We're getting a little more than we want on this right-hand rectangle. As we increase the number of rectangles, right, this approximation is getting better and better. So I've stopped at 50, right? And so if you notice along this left edge, we're getting these little extra pieces up above. In here, it looks like we're missing a little bit. We're getting a little extra here. So eyeballing it, this is still probably an over approximation, but a much better approximation than that first one, right? Let's see if we can go a little higher before we break the computer. Let's go up to 500 and see how it handles it. So now I'm just continuing to add approximations. And at this point, the computer has given up and just drawn it as the area. So if we zoomed in, right, we still are getting these little tiny bits above the curve, right? But that is a much, much, much more livable with error on that approximation, okay? That's what we do. This whole idea of what we're going to talk about for the next few videos, for many videos, is really at its core using approximating rectangles to get a handle on this kind of curved area, right? So we're using something simple to do something very complicated, right? If you look back at derivatives, the idea there was something very complicated. We used a very simple idea, slopes, to capture it, and then we added this limit in there. And that's exactly what we're going to do with this area idea. We're going to take a very complicated idea, approximate it with something simple, and then use limits to get it to meet up with that complicated part. So let's do a little example of some approximating to finish this out. So here's a graph of y equals x squared. Okay, let's put that on here. This is the function y equals x squared. And let's say I want the area under the curve between 0 and 1. So I've shaded that blue here to make it clear the area we're talking about. Okay, and you know, we're zoomed in, it looks almost straight, but there's a bit of a curve to this, so it's not quite a triangle. So we're going to try this approximation using rectangles. So here's our process. Okay. So I'm going to start with, I'm going to look at the section, I'm going to look at this section from 0 to 1. Let's make that a little thicker maybe. Let's see. So I'm looking at the number line from 0 to 1. And I guess it won't let me. Anyhow, looking at the number line from 0 to 1, I'm going to decide how many rectangles I'm going to use. And to start off simply, I'm going to use 2 rectangles, which means I need to divide this interval from 0 to 1 into 2 pieces. And also to make things simpler, I'm going to use the same size pieces, meaning I'm just going to cut this interval in half. So right at 0.5, I'm going to make this section here from 0 to 0.5, one base of one rectangle, and then this section here is going to be the base of the other rectangle. Okay, so there's the bases of the rectangles. The next decision I have to make is, where are the heights, right? So remember, we're trying to approximate this function. It would make sense to pick the height of the function, except the height of the function is changing across this whole interval. So I'm just going to pick, we can pick any point in the interval, right? The common choices are the left-hand side, the right-hand side, or the midpoint. So in this case, we're going to do the left-hand side, meaning for each of these intervals, I go to the left endpoint and I draw the rectangle whose height is the value of the function at the left endpoint. So for instance, in this first interval, the left endpoint is 0. The height of the function at 0 is just 0, and I have just this line as my rectangle. At 0.5, the height of the rectangle, this is going to be for my second rectangle. This is the left endpoint of the second interval. I go to the height there and I draw this rectangle. Okay, so it looks like there's just one rectangle because our first rectangle is has a height of 0. But let's compute this first approximating area. So I'm going to use some notation here. I'm going to call this L2. This is the approximation to the area we want using the left endpoints and 2 rectangles. So I'm putting all that information in this. So how do we figure out this area? Well, I have 2 rectangles. Each rectangle has a base of 1/2. I just multiply by the height, and the height is going to be the value of the function at the left endpoint squared. For instance, this one is 0 squared, this one is 1/2. So let's look here. I've got this point here is the height. It has x coordinate 1/2. Because it's on the curve y equals x squared, it means this y coordinate, which is the height of this function, is going to be 1/2 squared, or 1/4. Let's write it like this. Okay, and so you can work this out and we get 1/8. And that's our first approximation. Now, we look at this thing, it's not a great approximation. You can see how much area I'm missing, right? All this blue above this rectangle on the right and all this blue above the axis here. So let's try something a little different. Let's now do approximating rectangles, except use the right endpoint. So I've got the same intervals. Now I'm going to make a rectangle whose base goes from 0 to 0.5, but its height is now going to be the height of the function at 0.5. So my rectangle is this one. Okay. And then for the interval from 0.5 to 1, I'm going to use the right endpoint. So the right end of this interval is 1. The height there is all the way up at 1. Right? So I'm using the right, same interval on the bottom, but I'm using the right endpoint, I get this rectangle. Right? Now looking at this, I see that I'm making an over approximation. These rectangles are both larger than the area I want. Let's compute this. So I'll call this R2, same idea, right-hand endpoints, 2 rectangles. So my first rectangle is now, the base is still 1/2, same number of rectangles, times the height at the right endpoint, which is the value of the right endpoint put into the function, right? This point here, the next, right? We got this point here, which is 1, 1. Again, it's 1 squared. We're putting in 1, which is of course 1. And if you work this out, you get 5/8. Okay. Now what do we know from this? Well, what I think makes pretty clear intuitive sense is the actual area we're talking about, that blue shaded region, is between these two numbers. Okay. So let's put a little, I'm going to convert to decimals because in a moment we're going to get some fractions that aren't quite so easy. What we've determined is that our area is between 0.125, 1/8, and 0.625, 5/8. Right, so that's kind of our first result here. We've got an approximation. In fact, we've got a region, an interval of approximation where we can say the area is between these two values. Okay. Great. Okay, this is our process. This is a very simple version of our process, but this is the process. Let's make better approximations. So remember that image I showed you a few moments ago. One way we made a better approximation was by making more rectangles. So let's start this whole thing again, except this time we're going to make twice as many rectangles. Oops, it's still y equals x squared, but I'll just leave that off for some space. So let's see what we can do here. First, let's divide up the interval. Our interval is from 0 to 1. Instead of making 2 rectangles where we just divided it at 1/2, let's make 4 rectangles. Okay, exact same idea. Let's start with, we're going to do L4. Using the left-hand endpoints, I want to make 4 rectangles. Oops, let me do that a little better. So my first rectangle, the left-hand endpoint is at 0, so its height is right there. Here's my next interval from 2.5 to 0.5. The left endpoint goes up this high. We get that. At 0.5, we go up to here. And at 0.75, we'll go up to here. Okay, so let's put in these points. We've got 0, 0. So here we've got 1/4 is the x-coordinate. The height is the value of the function at this left endpoint. 1/4 squared is 1/16. Here we're at 1/2. Let's do 1/2. 1/2 squared is 1/4. Here we're at 3/4. 3/4 squared is 9/16. And we don't need this one right now, but I'll just put that in for consistency. All right, so there are our endpoints. I want to move this just slightly for reasons we'll see in a moment. Okay, so how do we compute L4, the area of these approximating rectangles? Well, this first rectangle has a width of 1/4 and a height of 0. The second, right, they're all going to have a width of 1/4. The height at this point is 1/16, right, which was 1/4 squared. Let's actually write it that way. I think that might help later. So this is 1/4 squared. We get the next rectangle, which has a width of 1/4 again, but now the height is at 1/2 squared. And then 1/4 times 3/4 squared, right? So we're just taking the value of the function at the left endpoints to get these heights. And if you work this all out, we get an uglier, we get 7/32. And let's just do this as a decimal. It's going to be about 0.22. Okay. All right. Same idea now. We're doing the right endpoints. So now I can draw in these rectangles, right? Again, notice that the red rectangles are all below the actual area. These green rectangles are going to be above, right? This isn't always the case that the left and right behave this way, but in this particular one, that's what's happening. Right? And so now I have 4 rectangles here. So, same idea. The first right endpoint rectangle has a width of 1/4, but now the height's not 0. I looked to the other side and got a height of 1/4 squared. The next right-hand rectangle has a width of 1/4 and a height of 1/2 squared. That's this rectangle going up to a height of 1/4, 1/2 squared. Then we get 1/4 times 3/4 squared plus 1/4 times 1 squared for this last rectangle. You can work this out. We get 15/32, or approximately 0.47. Okay. So notice what happened. Let's write this down. We now have an approximation for our area that says it's got to be bigger than the area of these red rectangles, right? Those are all below. And it's got to be smaller than the area of these green rectangles. They are all above it, right? So that blue area is pinned in between those two things. And notice, comparing this to what we did a few moments ago, it's still not a great approximation, right? There's a fairly wide amount of area that we can cover in here, but we've made the lower bound higher and the higher bound lower. In other words, we've squeezed that approximation a little closer. We used to say the area is between these two numbers. Now I could say it's between these two numbers, right? We've gotten it a little bit better, okay? I won't make you watch me do this for more rectangles, but something interesting happens as we do the same process over and over and over again. So let's do this. Let's let n equal the number of rectangles. Okay. So what I did was compute the left-hand approximation and the right-hand approximation for n of 10. So we just did 2 and then 4. I did it for 10, 100, and 1,000. Okay, now I didn't do this by hand. I programmed a computer to do it for me. As we'll see as these videos go on, we can put these into some nice compact formulas that computers can work well for us. So doing that left-hand approximation, I got 0.285 for 10 rectangles. And for right rectangles, I got 0.385. We got 0.328 for our next approximation, and 0.338, and then finally 0.3328, 0.3338. Okay, so notice how much closer that's getting, right? I should have put in one more category here. Our well, let's do this actually. I think I can make this happen. Whoops, that's not what I wanted to do. I think this is going to work. All right, I missed one line. I can repair that. So let's just put in that the last approximation we had for 4 with 4 rectangles. We had 0.22 and 0.47. So look, as we jumped up to 10, how much narrower this interval was, right? Remember, our area is always pinned between these two numbers because of the geometry of that picture. And you might notice that it appears that we're getting closer and closer to something, right? A possible guess, I'm going to put a question mark here, is, are we getting closer to 0.3 repeater, right? Or 1/3, right? I'm just noticing the pattern here. This is a guess right now. It's not mathematically sound to say it kind of looks like that's happening, but it does kind of look like that's happening, right? So it's a reasonable intuition and something worth investigating. So let's do one last thing with this idea to see if we can be a little more sure of this somewhat reasonable guess, okay? We're going to generalize this a little bit, meaning, or what I mean in this case is, I'm not going to use specific numbers. I'm going to see if I can come up with a formula that tells me how big the area is, or what the area is for these approximations, given a number of rectangles. So let's do it. It might make more sense. I don't know if that sentence was helpful. So I'm going to do right-hand approximations only. I'm just going to do one of these, and we'll see what happens. So here's a number line, right? So, oops, don't want that. Let's get this, okay. So here's 0, here's 1, right? So I'm not drawing the whole graph yet. We'll have to sketch a little bit of a picture of that in a moment, but I just want to start by dividing up this number line, okay? So I don't want to pick a number of rectangles, right? So I want to arbitrarily draw these, and I'm leaving it blank in the middle, sort of to indicate that these aren't the actual size of them. I'm just trying to indicate I'm just chopping it up a bunch of times, some general amount of times. Let's say, like we have here, n is the number of rectangles. If I were to chop this into n rectangles, how big is each rectangle? Well, let's just remember, when we did 2 rectangles, we took 0 to 1 and cut it into 2, we cut it in half. When there was 4 rectangles, we cut it into 4 pieces, we got 1/4 for the size of each piece. So for each rectangle, or for n rectangles, the width is 1/n. Right? That's how big each of these is. If I did 1/10 or 10 rectangles, I'd have 1/10 plus 1/10, 1/10. After 10 rectangles 1/10 long, I'd have an interval of 1. Okay? So that's the first idea we need. We need a little more space here. Okay. So let's write something in here. Our first, we start at 0. This next value is going to be 1/n. Actually, let's write them on top. Right? Because I'm moving over by a width of 1/n. I started at 0, I moved over by this width. I moved 1/n over. I'm going to move 1/n over again, and so I'm going to have 2/n. Then the next interval endpoint is 3/n, then 4/n, all the way up to, right, 1, which is just n/n. The one before it is going to be n minus 1/n, right? So again, it might look a little confusing, but if you put numbers in, if we divided this into 10 intervals, we'd have 1/10, then over to 2/10, then 3/10, and 4/10. We'd have 9/10, and then 10/10, or 1. So this is like the general idea that we have n intervals. This is a formula for each endpoint. Okay. If I wanted to figure out the approximation for n rectangles using the right-hand endpoint, let's look at what this first rectangle would be. Well, its width is 1/n. Its height is going to be the height of the function at 1/n. What's our function? We square the x value. So the height is 1/n squared. Now the next rectangle. All right, it has the same width, but now its height is 2/n squared. Then the next rectangle, 3/n squared, and we do this all the way up to 1/n times n/n squared. Okay. All right, let's do a little bit of algebra to this thing, right? I get 1/n times 1 squared over n squared plus 1/n times 2 squared over n squared plus 1/n times 3 squared over n squared plus 1/n times n squared over n squared. I can pull out an n squared and the 1/n from all of these, so I get 1/n cubed, and I have 1 squared plus 2 squared plus 3 squared plus n squared. Okay, so I'm just doing some algebra, right? Just if we add up a bunch of numbers, if they all have a 1/n cubed, I can factor that out, and then I've got this thing left here. Okay, so what I'm looking at right here is a formula for if I choose n rectangles and I create, if I divide up the width from 0 to 1 into n intervals, and I create rectangles using the height at the right endpoint, this formula right here will tell me the area of those approximating rectangles. Right, so if I put in 7, I would do 1/7 cubed times 1 squared plus 2 squared plus 3 squared up to 7 squared. And that would give me that formula, right? All that work we did in the first one, this is a simpler, compact formula. I'm going to use a formula without justifying it right now. I'm going to encourage you to check it on your own. This formula is, let me just write it off to the side here. If you take the sum of the first, oops, I already skipped one, I can't count. If you take the sum of the first n integers squared, meaning this, it's the same as doing n plus 1, 2n plus 1 divided by 6, right? So try it. If you wanted to do, let's do one of them. If we did 1 squared plus 2 squared plus 3 squared, I'm claiming, so this is going up to n equals 3, this is equal to 3 times 3 plus 1 times 2 times 3 plus 1 divided by 6. Well, the left-hand side is easy enough to do. 1 plus 4 is 5, plus 9 is 14. Over here, we get 3 times 4 times 7 over 6. And if you look closely, this is, I can divide this by 2, cancel a 2 there, then cancel the 3's, and I've got 2 times 7 is 14, right? So of course, I'm not proving it to you, but I'm just, you can try it for a few more numbers. This is a known formula. We'll look more closely at it later. But for now, I just want to use it. So I can substitute this formula in for this piece I have in the parentheses. The sum of the first n squares is n times n plus 1 times 2n plus 1 over 6. We can expand this formula and write it as, let's do a couple things. I can cancel an n with this n out front, so my denominator becomes 6n squared right? Canceling this 3 with this. And if I expand the top, I get what? 2n squared plus 3n plus 1. Okay, so here is an even better compact formula for the area of the approximating rectangle. So if you wanted to know right now, and in fact, this is what I did to get these, you can plug 1,000 into this formula and see the Rn, the formula for Rn will pop out that decimal, okay? Now, it's still an approximation. So let's do, let me clear some space. Let's do one more thing. Remember that one of the first images I showed you, and the idea was if we just continue to make more and more rectangles, we get closer and closer to the actual area that we care about. In other words, what happens to this number, or what happens to this formula? What happens if I make more and more rectangles? In other words, I get n to be larger and larger and larger. In other words, I want to take the limit as the number of rectangles goes to infinity. Right? We guessed, looking at those decimals, that it seemed like it was getting closer to 1/3. Let's take a look. We've now got an expression, right? For every number of rectangles we choose, the area looks like this. Let's take this limit and see what happens as n gets larger and larger and larger. You might remember some tricks for this. Let's just do a little bit of algebra. I can split this up into 3 fractions. We get 2n squared over 6n squared plus 3n over 6n squared plus 1 over 6n squared, which is the limit as n goes to infinity of 1/3 plus 1 over 2n plus 1 over 6n squared. Probably a good time to remember our limit laws. I can take each of these limits individually. The limit of a constant, so the 1/3 doesn't change as n gets larger. 1 over 2n becomes smaller and smaller and smaller. Its limit is 0. 1 over 6n squared, same thing. Oops, I wrote 1 over n. That was supposed to be the 1/3. And in fact, we see that this limit, as n goes to infinity, of these right-handed rectangles is 1/3, okay? In other words, what we're saying is if you keep making better and better approximations, more and more rectangles, so the bits of area that you're missing are less and less, or in this case, the bits that are above are less and less, you will only get closer to 1/3. Okay. We could do the same thing for those left-hand endpoints. It'll be a very similar process. I'm gonna leave that. You're welcome to try that one on your own. You'll be able to do it pretty easily after a few more videos, maybe already. Those two numbers, the left-hand endpoints and the right-hand endpoints, are going to both be squeezing in to 1/3, right? They're never going to get there, but they're always going to be getting closer to it. And that's what we'll take the area to be, right? The area, what I'll say to finish is that we're going to use this as our definition, right? There's a little more to do, but we'll do that in later videos. But this is the big idea, that the area under the curve, remember where this all started, y equals x squared from x equals 0 to x equals 1 is 1/3, right? That's how we'll make sense of that curved shape, as we referred to rectangles and took a limit, right? So it's very, very, very aligned with our thinking in Calc 1 in differential calculus, where you say, I have this idea of a slope, and I'm going to take a limit to get this instantaneous rate of change or slope at a single point. One more clarification before we finish. I just want to be clear about the area under the curve. It's the phrase we often use, but what we really mean is the area between the x-axis and the function, okay, when we graph it. So that's the area we're talking about. Okay, that's it for this one. We will generalize this even more in the next few videos. And then maybe a little preview is in order. If you recall from differential calculus, you take these limits. It can be a very complicated process. We're going to go through something very similar, and then we're going to find a way to shortcut this whole thing, just like we developed rules for taking derivatives. When you learn them, you don't have to refer to the limit every time. You can develop a bunch of rules. That's very similar pattern we're about to see when we go through this area problem. Okay, that's it for now. Thanks, everybody. See you next time.